Alright, so here is part 5, and this should be the end of the multiple choice, and then we'll get into the free response. So, a marketing company reviews the length of television commercials, monitoring a random sample of commercials over several days. They found a 95% confidence interval for the mean length of commercials, which was 23 to 27, which is true. Okay, so we're 95% sure that the mean commercial length, this is our model sentence, right? So 20 is A. All of the rest of them do not follow the model sentence, and so all the rest of them are wrong. Okay? 95% of commercials they checked, no, right? That doesn't necessarily have to be true. 95% of all commercials aired, no, right? We're talking about where the mean length is. It's 95% of all samples. Oh my God, all samples is not what a confidence interval is all about. And commercials average between 95% of the days. Ugh, no, no. All right, so here we go. 21. Which of the statements correctly compares T distributions to the normal distribution? T distributions are also mound-shaped and symmetric. I think by mound-shaped they mean unimodal. Okay, and so this one's going to be good. All right. T distributions have less spread than the normal distribution. No, this is false. Remember, they have fatter tails, and so they actually have more spread to account for the small sample sizes having more variability. As degrees of freedom increase, the variance of T distributions becomes smaller. Yeah, the variance becomes smaller because it becomes more and more and more like the normal distribution. The fat tails get skinnier and skinnier. And so that's going to be okay. All right. So the answer is 1 and 3. And so 1 and 3 is E. All right. Doctors at technology research facility randomly assign equal numbers of people to use the computer keyboards in 2 rooms. In one room, a group of people typed a manuscript using standard keyboards, while the other room people typed the same manuscript using ergonomic keyboards to see if those people could type more words per minute. After collecting the data for several days, the researcher tested the hypothesis, right? So we have our correct null hypothesis that there's no difference in the mean words typed against the one-tail alternative. What would be the one-tail alternative here? I mean, it's a good thing to write these things down. That the alternative hypothesis would be that mu1 minus mu2 would be less than 0, right? Because they want to actually discover whether the ergonomic keyboard was better. That means a bigger score, more negatives, is going to be less than 0, okay? So, wow, as I'm looking at that, that looks like crap. So I'm going to redraw that, but I'm not going to re-explain it. Okay, so the alternative hypothesis is mu1 minus mu2 is going to be less than 0. Okay, so obviously I don't know this until I check all the rest of them. There's a 22% chance that there's really no difference in typing speeds. Again, really what we're doing with the p-value is we're comparing the distance away one from the other. So while there is a 22% chance, it's not that there's really no difference, okay? There's a 22% chance another experiment will give the same results. This experiment does not affect another experiment in the way that we're measuring the p-value, okay? People using the ergonomic keyboards type 22% more words per minute. Okay, so this is probably going to be false, right? Because actually a large p-value like this would mean that we would reject, that we would fail to reject the null hypothesis. So we're going to fail to reject, which means people using ergonomic keyboards didn't really type more words per minute, all right? Not that that's really what the p-value means, but this is just a false statement. There's a 22% chance that people using ergonomic keyboards type more words per minute. No, I mean, this is probably the closest one, but really it's a 22% chance of observing people using ergonomic keyboards having that mean given that there's no difference. So again, there's some language that's missing from here, and so A ends up being the correct answer. And again, really, none of these are a conclusion, right? We would write. And so because none of these are really a conclusion we would write, none of these really follow the definition of what a p-value means, which was from our very first video, our very first question. I have to say it's none of these. All right. Like I said, the language is very close, but there's some really important missing elements. All right, 23. In an experiment, the primary purpose of blinding is to reduce bias, right? We blind to prevent reporting bias. Not randomness. Blinding doesn't take care of randomness. Blinding doesn't take care of variation. Blinding doesn't take care of confounding. And blinding doesn't take care of undercoverage. Blinding takes care of bias. And then 24. At least one SAT test site students taking the test for the second time volunteered to inhale supplemental oxygen for 10 minutes before the test. In fact, some received oxygen, but others, randomly assigned, were given just normal air. The test results showed that 42 of 66 students who breathed the oxygen improved their SAT scores compared to 35 of 63 students who did not get the oxygen. Which procedure should we use to see if there is evidence of breathing extra oxygen can help test takers think more clearly? Okay, so what are some of the things that we're looking for between a z-test and a t-test? Well, we're looking for the difference between mean and proportion, right? And okay, so are we talking about a t-test or a z-test? And so students who breathed oxygen improved their SAT scores compared to students who did not get the oxygen. If you look at this, this is 42 successes out of 66. This is 35 successes out of 63. And so what's going on here is you have the P, right, of oxygen is going to be, the P hat of oxygen is going to be equal to 42 out of 66 successes versus samples. And our P hat of air, right, is going to be 35 out of 63, right? And what we're looking for, our null hypothesis, is going to be that P of oxygen minus P of air is going to be equal to 0, that there's actually no difference. These are proportions, and there are two proportions, and so what we're doing is a two-proportion z-test. Obviously, with two samples, right, we're not going to have a one proportion or a one sample, right? And I don't think this follows the matched pairs, and we didn't really talk about it, so that wouldn't be an answer anyway. So really, you're just trying to determine whether it's a t-test or a z-test, a two-sample or a two-proportion. If you just looked at scores, like I started to do, okay, you could make a mistake here. But I think the big thing to focus on is that you had 42 out of 66 students who improved, and then you had 35 out of 63 students who improved, all right, and so who improved, right? And so those are proportions, right? 42 of 66 is going to be like this. All right, so be really careful about how you read these, because I initially started to do this wrong. Okay, so now 25. A statistics professor wants to see if more than 80%, here let me change colors, of her students enjoy taking a class. At the end of the term, she takes a random sample of the students from her large class and asks in an anonymous survey if the students enjoy taking a class. Which set of hypotheses should she test? Now, obviously it doesn't say anything about, you know, any sort of reporting bias or voluntary bias or anything like that. She just wants to see if 80% or more of her students enjoyed taking her class. So you either did enjoy or you did not enjoy, so that's going to be a proportion. The null hypothesis is always equal to, so this one's possible, not this one. This one's possible, not this one. So we're only looking at B and D, and the more than 80% is going to lead us to a greater than right here, and so 25 should be D. All right, and that's going to conclude part 5. That's going to conclude all of the multiple choice. That makes us really happy. See us later as we do the free response.